Hey there YouTube, Paul here from theengineeringmindset.com. In this video we're going to be looking at the centrifugal compressor as part of the centrifugal chiller series, and we're going to be looking in quite detailed explanations about the operation of the compressor and why it's important and what it does for the chiller. Now obviously the compressor is the driving force of the refrigerant around the system, and we'll have a look at some worked examples and also some real life photos, etc., of exactly how this is working. Now if you haven't watched the other videos in this series on chillers, then I'd really recommend you go back first and take a look at these and take some notes and really build your base knowledge, as this is a fairly advanced step, and you should really fully understand the operation of a chiller first before moving on to this section. Now the chiller, as you should know, the compressor, sorry, as you should know by now, is mounted up here on the top of the chiller, and it's being fed on the suction line here from the evaporator, and that's the refrigerant leaving there, boiling off and entering through the suction line into the compressor, just passing through the vane guides here. And the refrigerant's then going to enter the compressor. It gets spun around at high velocity and compresses in the volute here, and then that gets sent down into the condenser here, and the heat is then rejected from this and off around the building. A real world example of the compressor and how it would look if you walked into a plant room would be like this. So as I was saying, you've got the suction line and the discharge line here, and on the very top you've got the compressor hidden behind all these cables and pipes in this example. There's another example here of a much larger and older chiller with, again, it's mounted on the top here. It's just a slightly older version, and it's using a different refrigerant, and you can tell that by the size, but we'll have a look at that in detail later. And I've also got a thermal image from one of the chillers we were working on previously. And as you can see from here, the discharge line is coming down here with the suction line here, and this is the hot refrigerant, condensed, compressed even refrigerant coming out and entering off into the condenser. So what does the compressor do in the chiller? Well, the compressor is absolutely essential for the chiller to operate. Now the compressor is going to compress all the particles of the refrigerant together, and that moves all the energy. It makes it really highly energetic, and really increases the temperature, and that is absolutely key to the operation. Now if you imagine here we've got just a beacon or a glass, and say we put a lid on it which we can move, and we fill it with some refrigerant particles. Now as we move this lid and push it downwards, you'll see the particles become more closely packed, and they'll start to change color, indicating they're getting hotter. Now they're becoming really closely packed, and then it's finally at the very last point where all the particles are completely next to each other, and there's a lot of energy in there. A lot like if you was to hold a bike pump and hold the end of it. As you push the piston down, the end of it heats up. That's all the particles moving together and really giving off that heat. A bit like maybe a busy train. If you start pushing a lot of people in there, it all gets a bit hot, a bit noisy, a bit sweaty. No one likes being that close to other people. They can't move around so much, and they get a bit agitated. So it's just going to raise the temperature and the energy in that, so it makes everything much more dense and much more compact. And the reason that's really important is because, as you know from the kind of layout here of the chiller, we're picking up about 6 degrees Celsius on the chilled water as it's going up and picking up the heat from the building. We've got to take that heat from that circuit and move that over to the condenser circuit. Now heat flows from hot to cold, so in order for us to extract the heat out of the chilled water loop and move it into the condenser water loop, we're going to have to make sure that the refrigerant that carries over there is entering the condenser at a higher temperature than this return water. So you can see it's coming in, or it's coming back from the cooling tower about 27 degrees Celsius. That means the refrigerant, in order for the evaporator to reject heat, the refrigerant coming into the condenser has to be hotter or at a higher temperature than 27 degrees Celsius in this example. And the only way to do that is to compress everything, compress all the particles, raise that temperature, get the energy in a much denser form so that it can be moved more efficiently, and we can transfer that heat. If the refrigerant entering into the condenser was at the same temperature, say it entered at 27 degrees Celsius, you wouldn't reject any heat and the chiller would not work. This water would go back out at 12 degrees and come back at 12, probably even higher than that, and eventually the chiller would just drip out. So let's have a look inside the compressor, the centrifugal type, and see how it works. So if I just isolate this part of the chiller, and start to strip it down, and we'll have a look inside the components. So here we've got obviously the discharge line coming there, and the suction line would be coming in and entering here where the refrigerant enters, and I've just removed those sections there so we can start to look inside. So underneath the first part of the cover, we've got the vane guides there, which do the capacity control. We've got another video on that if you want to learn how the chiller capacity is controlled. And behind that we've got the inlet shell, and then we come down to the actual compression chamber, exposing the impeller here, along with the diffuser, which is just here in between the compression chamber and the volute. The volute is this area here, this spiral around the perimeter of the compression chamber, and I'll just show a different angle there so you can see a bit better. So here we've got the impeller, and this gap in between is the diffuser. Just a small gap running between the two. If you look inside the pipe there, it's inside the discharge pipe, you can see that obviously that is the same color, where it's the inside of that shell. And if I just do a section view on the compressor chamber there, just to show you, so we've got the motor sealed at the back here, and that is driving the impeller here, and that's just a gear mounted driver there directly off of the motor. Rotates through this, and then that then in turn rotates the impeller, which sucks the refrigerant gas in, and then we're going to distribute that out at a high velocity out through this diffuser. If you look at the impeller here, so you can see we've got the gear mounted on the bottom of the shaft there, and at the top we've got the inlet or the flow area, and then we've got a shroud here, and then just hiding the blaze behind it. And if I remove the shroud, you can just expose the blaze there, and you can see the kind of shape they've got. So this will suck the refrigerant in, and it will divide the refrigerant that's coming in into equal portions and distribute that off through each of these blade discharge areas. And you can see it's a backwards inclined blade, which sends it off at a high velocity. So if we looked at the impeller from the side view, just to make you understand, so the refrigerant would be sucked in from that top area, and then it's going to flow through these channels and then out towards the diffuser. So it comes in from the evaporator in through the suction line, and then gets forced in, split up into multiple sections inside the impeller, and the blades then compress this and throw it out and send it off down at a high velocity out towards the condenser. So as you can see, the refrigerant coming in there, hitting into the blades. I've just done a section view on there so the blades aren't in full, and it will take this path and then make its way out through the diffuser into the volute, and then out into the discharge line. And there's another view of it there with the arrows indicating the flow path as the particles of the refrigerant are split up and forced through these different sections as this is rotating also a very high angular velocity. And just the diagram here to show you an animation, even to show you kind of the flow path of that, so you can see it's being flung off of these blades here and pushed out, and then that momentum is forcing that all the way around the volute and building up that head pressure. Now in this section view you can see the diffuser much clearer. So the diffuser is this thin channel here between the impeller and the volute. See this gap here. So as the refrigerant would flow into here, and this is spinning at a really high angular velocity, and it spins that refrigerant out, spits it out, and then passes through this diffuser before all the refrigerant then collects up in this volute, and also obviously down here as well. And it's going to flow like this round in a spiral shape round to the discharge line. Now the purpose of the diffuser is to simply slow the refrigerant down, and as it does so, it converts all the refrigerant's kinetic energy into static pressure. And this increase in pressure is known as the lift. And that's also known as the head pressure. Now lift and head pressure, and static pressure in there, this is really, all it is just the difference between the pressure of the refrigerant in the condenser and the pressure of the refrigerant in the evaporator. That's literally it. So what's happening to the refrigerant as it enters and gets flown around by the compressor? Well, we know that when the impeller spins, it's going to have an angular velocity, right? And another key aspect of the compressor is also the diameter of the impeller. So these can vary in size, and the reason it varies in size is due to the type of refrigerant that you're using. So different refrigerants will have different molecular weights, and also the amount of lift or head pressure you want to create, and the amount of refrigerant that you also want to flow through the chiller, producing the cooling effect. So the size of the impeller is also really important, and we're going to look at some equations shortly. So we're just going to use this letter R to indicate the radius of that impeller. Now let's imagine we've got a particle, a ball of refrigerant, and it's sitting just at the very edge of the impeller, just as it's about to be thrown off and chucked through the diffuser and into the volute. So this is the point where the maximum centrifugal force is applied to this mass. So that's the point of interest and what we want to focus our formulas on. Now you should know that if you spin something, it wants to move away from the center as far as possible. So much like if you had, say, a stone or something tied to a piece of string and you spun it around, that object moves to the outer edge. It tries to move as far away as possible from the center. So we're going to have this line here, which is the centrifugal force, and we're going to represent that as the green line here, and that's the force moving out, trying to push away from the center. The second force, which would be occurring on this mass as it spun around, is the tangent velocity, and we can see that as this pink arrow here with the letter V, and that is because as the mass is spun around, rotated around the center, it's got a mass and it's got inertia, so it's going to try to continue moving this way as the force, centrifugal force, tries to push it out, which would leave you obviously in a resultant force, but we'll look at these two for now. And I'll just put the symbols and titles and units down the side here just for your own reference. These are the formulas we're going to look at. Just remove that squared root there, we shouldn't have that. But let's have a look at some examples. let's say the refrigerant has a mass of 1 kilogram. The impeller is rotating at 120 RPM, revolutions per minute, and the impeller has a radius of 0.25 meters. So this is the formula and the calculations you would use to work out the centrifugal force and also the tangent velocity. And as you can see, if we had 1 kilogram rotating at 120 RPM, this would result in 39.4 newtons, and that would also result in 3.14 meters per second as a tangent velocity. So what happens if we double the radius of the impeller? Well, as you can see, the centrifugal force has doubled, and so has the tangent velocity. So the size of the impeller is important. But what happens if we keep the radius the same as the first example, but we increase the speed, or the rotational speed, of the impeller? Well, as you can see, we'll get the same centrifugal force at 169.5 RPM as we did with a radius of 0.5 and a speed of 120 RPM. But we will not reach the same tangent velocity because obviously this has a higher tip speed. So the speed and also the diameter are very important characteristics of the impeller and the chiller design. Now you can see from this photo here that this chiller is a very large chiller. It's using a very large compressor, and the diameter is obviously very large as well. And that's because it's using an older type of refrigerant. It's got a higher cooling capacity, and will run at a different speed compared to this next one, like this one here. So this is a much smaller one. This is for an office as well. The previous one was also for a large office building, also some data centers and stuff on the floors, or MER rooms, comms rooms. And this is just for offices, so it's a lot smaller. It's a much newer model as well, of different manufacturers. But here's one more really small chiller. We've got the compressors down on the bottom here. This is a different type of chiller. It's not using centrifugal force, but just to give you an example of how small chillers are and how big they are really. You can also see here where one of our chillers was stripped apart, and you can see inside the actual chambers here. So the front view here, so you can see inside the volute as it's going, it would flow through and down into the discharge line. And there's also a section view here of the inside of the compressor unit. So you can clearly see here the inlet from the suction line going into the impeller section here. We've got the impeller there. We've got the volute, which is in this region here. Then the discharge line just here. The diffuser is this small section just here. And then just at the back here, we've got the impeller shaft, and you can see the gear just there. And then obviously we've got the main gear here, which is connected via this shaft here, which goes directly to the induction motor mounted at the back of the chiller. So how much work is done by a compressor? Well, you can calculate that, because the difference, or the energy used, is the difference between the suction line and also the discharge line, and it's the difference in enthalpy between the two. And the formula we'll use to calculate this is like this, and the letters for that is obviously W equals work measured in kilowatts, H, you got H1 and H2, and that is the enthalpy, and that's measured in kilojoules per kilogram. And then the M, which is the mass flow, which actually should be a dot above that, but that is mass flow per kilograms per second. So the amount of energy used is the mass flow rate multiplied by the change in enthalpy across H1 to H2, or H2 to H1, between the suction and discharge line. So let's say the refrigerant flow rate is 3 kilograms per second. That's the mass flow rate. You can see it's color coded in green there as well. So per second there's 3 kilograms of refrigerant passing through. And the difference in enthalpy, the discharge is 420 kilojoules per kilogram, and the inlet is 396 kilojoules per kilogram. So for every kilogram going in, remember there's 3 kilograms there, that means there's 396 kilojoules going in, and there's 420 kilojoules per kilogram coming out. So it's much more densely packed. The enthalpy has been compressed in there. So we can calculate that, so we can fill in the numbers, and work equals 3 kilograms per second times 420 kilojoules per kilogram minus 396 kilojoules per kilogram. That leads us to 3 kilograms per second multiplied by 24. That's the difference in these two, and that results in the work being done as 72 kilowatts. Alright, that's it for this video. Thank you very much for watching. If you found it useful, then please like, subscribe and share the video. Any questions, leave them in the comment section below. I'll try to answer them as soon as I can. Don't forget to check out our website. We're also on the Facebook, Twitter, Google+, etc, etc, etc. So thank you for watching.